Hi, my name is Florian Niedermann. I'm junior faculty at Nordita in Stockholm. And today I want to talk about an early universe alternative to evolving dark energy. You might have all heard about the claims made by the DESI collaboration that observations of baryon acoustic oscillations provide evidence for evolving dark energy. And here I want to come up with an alternative explanation which relies on new interactions in the early universe. This is work done in collaboration with Matthias Garni and Martin Slot, but also in parts with Henrique Rubira. Okay, let's start. And let me first remind you why baryon acoustic oscillations are such a nice probe in cosmology. And after all, this is the probe that gives rise to these claims about evolving dark energy. So in the early universe, there was this hot, dense plasma of photons, electrons, and mostly protons that are tightly coupled. And tightly coupling means that the interaction rate, for example, given by Thomson scattering, is much larger than the Hubble parameter. And this tightly coupled fluid supports its own sound waves, what we call acoustic waves. And a simple picture would be the following. If you look at a point perturbation in this fluid, then it propagates outwards like a spherical wave. And this wave is characterized by the distance it can have traveled by a certain time. This is what we call the sound horizon. And importantly, for these baryon acoustic waves, they freeze out at some time, they stall. And the reason is that electrons and protons recombination combine into neutral hydrogen, and this releases the photon pressure. So this system stops to be an oscillatory system. And this moment is called baryon, the epoch of baryon drag. Well, this sets this sound horizon scale. It's just an integral over the sound speed, as you would imagine. And importantly, this sound horizon scale imprints itself in the matter power spectrum of the universe, and this is what we can observe in the late universe at very low order unity redshifts. And it manifests itself, for example, in the galaxy correlation function, which shows this bump, which is the BAO peak. And importantly, the sound horizon scale sets the position of this peak. So for the BAO peak, for realistic values of that cosmology, you get roughly 100 megaparsec divided by little h, which is the dimensionless Hubble parameter. Importantly, what we observe is not the absolute scale itself. We observe its angular size. So it's the simple geometric picture. So we observe the ratio of the sound horizon and the distance, which depends on the late expansion history. So as I said, redshift order unity, and this distance is a function of Hubble. So this is how we learn about the late expansion history from these measurements. So we can learn about dark matter and dark energy. At least if we make that base assumption that the sound horizon scale acts like a universal standard ruler, and then we get this 2 to 3 sigma evidence for evolving dark energy using this newest DESI DR2 data. So here I want to argue for another possibility, namely that the statement about RD being this universal standard ruler is incomplete, and there might what we see might be the footprint of new interactions in the early universe. So this brings us to what is called dark acoustic oscillations. So these oscillations arise if you have dark radiation interacting with a fraction of dark matter through some dark force, which also leads to tight coupling. So what were photons before is now dark radiation. What was electrons, protons before is now a fraction of dark matter. And this system, as before, comes with its own sound waves. And then we have to extend our previous BAO picture. So now there are these dark acoustic oscillations which exist in addition, and they correspond again to these shells that expand spherically, at least in the simple picture. And they come with their own characteristic sound horizon scale, which can be larger or smaller than the one from the baryons. And in this galaxy correlation function, they would lead to a second peak. So in this case, the DAOs would freeze out at a smaller scale and lead to this green curve with this DAO peak, which in this case would have a smaller amplitude. But importantly, what we observed then, if you look for the BAO at roughly 100 megaparsec, is we wouldn't observe the BAO peak. We would observe the superposition of the BAO peak and the tail of the DAO peak. And this has some effect and changes the parameter inference we make. And we need to account for the DAO to then correctly infer the baryon sound horizon. That's the idea. So we do that by going to momentum space, then we deal with the galaxy power spectrum. We add a DAO part to that, which we model as a damped sinusoidal wave. So this is a very phenomenological approach. And then we can ask, how does the measurement change? So how do these angles we observe change? So we do, they are functional of the power spectrum. We do a functional Taylor expansion, and that gives us a shift in the angle if DAO are present. And that shift depends on the sound horizon scale of these DAO, but also their amplitude and their damping properties. And this is what we call the DAO bias correction. And if DESI gives us their data, and we believe in DAOs, then we need to correct that data to be able to actually extract information about the baryons. And if we do that, we can ask, do we get a better fit to data? And indeed we do. And interestingly, data is even able to single out preferred scales for this dark sector sound horizon. So we find what we call the negative branch. So there's a preference for a sound horizon at a roughly 60 megaparsec over H. So this would be the scenario I indicated in this cartoon here. But there's also the possibility for a DAO on the other side of that peak, but closer to the main peak, which we call the positive branch. And in both cases, the net effect is to shift the BAO peak to the right. In this case, you can understand it because it's only the tail that overlaps with the BAO peak, and the tail comes with this dip here, and the dip eats more away from the left flank of the BAO peak than of the right flank, which leads to a net shift to the right. In any case, then you get a fit improvement of 5 chi-squared units, which is not as good as the fit improvement you get for evolving dark energy, which would be more -10. And you might ask, how significant is all of that? And in fact, I mean, you might wonder, is there any independent evidence for these DAO at the right scale beyond this kind of first indication here? And the answer, interestingly, is yes. And it comes from CMB and the Hubble tension. And it gives rise to a prediction, which is this dotted line. And we were quite surprised when we realized that this independent prediction also prefers DAO, particularly the negative branch, at almost exactly the same scale. But 2 ingredients are required to getting these DAO. You need a sizable amount of dark radiation and interactions with dark matter. So how do we get that? Well, the idea is to get dark radiation from super cooling. And what do I mean by it? So there's a certain problem with dark radiation because there are bounds from Big Bang nucleosynthesis on it. So on the y-axis, I show the dark sector energy density measured in units of the energy density of a single neutrino, what we call delta N effective. And that is bounded by BBN. But now for the DAOs, you need a certain amount of the delta N effective, and it exactly corresponds to this, or well, not exactly, but roughly corresponds to this yellow dotted line, and it clashes with the BBN bound. And you also need that amount, by the way, to address the Hubble tension with CMB data. So the idea to get around this bound is the following. Imagine that the dark sector initially is very cool, so the dark radiation is very subdominant, but you also have a dark sector Higgs field, which sits in the minimum of its potential. And this potential is thermally corrected. But as the temperature further cools in the dark sector, just due to the expansion, and that potential reveals its true vacuum structure, and there's a second minimum, and the field is but the field is stuck in the false minimum, separated by the small potential barrier, which is still due to the remaining thermal corrections. This is what we call supercooling. Then the latent heat, the difference between true and false vacuum and potential energy becomes important. It acts like a cosmological constant. And relative to all the other energy density in the cosmic fluid, which goes down like radiation, it becomes more and more important. This is this yellow bit, and it increases the importance of the dark sector. But then a phase transition happens. The field undergoes sub-barrier tunneling, and you create bubbles of the true phase that expand, collide, and eventually decay into radiation and reheat this dark sector. And this is where the dark radiation comes from, which we need for the DAO and also to address the Hubble tension. That's the idea here. And you can think about it in rough terms as a dark sector analog of the electroweak phase transition, even though there are crucial differences. So we look at an SUN non-abelian gauge theory that is broken to an SUN -1. We also have first order phase transition, and everything happens at smaller energy scales. Any case, so as a particular model, we look at the hot new early dark energy model. That's the microscopic name we give the microscopic framework, and it's based on this SUN gauge theory with the weak gauge coupling. That's important, and we consider Coleman-Weinberg potential. So the crucial part about this potential is, I mean, it's a quartic potential which comes with at one loop order with log corrections, and these log corrections turn a simple monomial potential into one which has two minima. This is what we call radiative symmetry breaking, and there's then the second minimum with a non-trivial WEF, the symmetry breaking minimum, and it leads to breaking from SUN to SUN -1 when the field picks up its WEF. And the interesting thing about this Coleman-Weinberg potential is that it's very flat around the symmetric point. So its derivative and second derivative are vanishing at zero. And this means that it's very easy to inhibit the transition from the symmetric to the broken phase already when you have only a very small temperature, because the potential is so flat. So any barrier will prevent the field from tunneling. You have strong supercooling. This is a property of these potentials. And in our case, even too much supercooling, you would heat the dark sector too much. So we need what we do as a remedy, we introduce an explicit breaking term. It's this term here. And this mu effective is a dimensionful breaking parameter, which is technically natural because you have an enhanced symmetry when you send it to zero, but it gives us a dial to control the amount of supercooling we have. There are additional requirements we impose. We want the vacuum bubbles not to grow to cosmological size, because then they become a phenomenological liability. You would have maybe observed them in the CMB already. Just because they introduce anisotropies. This puts an upper bound on the gauge coupling. At the same time, we want this reheating after the phase transition of the dark sector to be very fast. This means the Higgs has to decay very quickly into massless gauge bosons, which make up dark radiation, which happens via these triangle diagrams. This puts a lower bound on the gauge coupling, and you are left with this viable window here. Okay, but what about dark matter? As I said, for the DAO, we need both dark radiation and dark matter. The idea here is that dark matter is now a fermion that is charged under that SUN, so it transforms in a fundamental representation, and you're left with the following picture of the dark sectors. There's dark matter, which we call chi, in this SUN multiplet. Then there's dark radiation, which is composed of the massless gauge bosons of that SUN. And there's a gauge force between the two components. And this is exactly what I showed you before, what we need for the DAOs. We have dark radiation interacting with dark matter, and that interaction is strong enough for tight coupling. But it's still a weakly coupled SUN. That's important. Okay, and at the same time, we have this dark sector Higgs field and the latent heat is associated with early dark energy. It acts like a cosmological constant. Then the phase transition happens, the supercooling goes on, but eventually the latent heat is converted into dark radiation, which now is composed of the remaining massless gauge bosons that still remain in this SUN-1. And with the dark matter, something interesting happens. It splits into two parts. There are the charged dark matter components, and there's a neutral dark matter component with respect to interactions with the remaining massless gauge bosons, so with respect to the SUN-1. So only the charged ones interact with the massless gauge bosons. But then there's an important quantum mechanics effect going on, and this is just something that happens automatically in that model. It's not something put by hand. I mean, you cannot avoid it. There is a mass splitting between the neutral and the charged ones, controlled by the gauge coupling. So the charged ones happen to be slightly heavier than the neutral dark matter components, and that makes it energetically favorable at low energies for the charged components to annihilate into the neutral ones. So you get a Boltzmann suppression. And this has interesting consequences because as the temperature further cools, once the temperature drops below this scale set by the mass splitting, the charged dark matter components, so the interacting ones, are depopulated, and there's only neutral dark matter left, and the interactions between dark matter and dark radiation turn off, they decouple. And that's crucial for these DAOs to form. I mean, for these shells to stall, essentially, and that then sets this sound horizon scale of the DAOs. And you're left then with cold dark matter, self-interacting dark radiation, and a contribution to dark energy. So how well does this model do with data? Well, we implemented it in a Boltzmann code with 3 additional parameters. So this would be the amount of dark radiation, delta N effective, self-interacting dark radiation. Then there is the fraction of dark matter involved in the interaction and this time of the decoupling. And then you can test this model, for example, against Planck data. And this posterior plot on the right shows what you get. On the y-axis, we have the dimensionless Hubble parameter. On the x-axis, the sound horizon scale. So first, and the color indicates the amount of dark radiation. So if there is no dark radiation, you're down here. That's lambda CDM. And you see its Hubble parameter is far away from this higher gray band labeled shoes, which is the locally measured value. And this is the usual Hubble tension and people talk about. But then if you allow for dark radiation, you see you bridge some of that distance. But for most values of the sound horizon scale, you only go up to here. So you do not fully resolve the tension. But then there is a particular range of values where you fully overlap with the shoes band without including any prior on that shoes value. And that makes both data sets actually compatible and allows us to combine CMB and shoes data. And if you do that, we get a prediction for this DAO sound horizon scale. So in other words, it's going to single out that peak region here, and these numbers is what you get. So the DAO sits somewhere between 50 and 70 megaparsec. And as I showed you before, this is exactly compatible with this negative branch of this very phenomenological DAO bias analysis we did. So this is what got us quite excited about this. But now ongoing work is focused on finding evidence actually for these DAOs in full shape data. For that, we decompose the wiggly part of the matter power spectrum into BAO and DAO parts, so you can do that, and then you see 2 damped sinusoidal waves as expected. But let me finish here. So this is my summary. It's exciting times in cosmology. There's a lot of new data coming in particular the Hubble tension, the BAO anomaly might be the signature of a supercooled phase transition with subsequent decoupling between dark radiation and dark matter. We call this DRMD. And this DRMD model comes with a falsifiable signature, which are DAO between 50 and 70 megaparsec over H. And well, at first, if you like, plausibility check through this DAO bias analysis was already successful, you could say. But now it's of course about looking for more evidence in full shape data and so on.